So this section is molar volume at STP. So STP is an abbreviation for standard temperature and pressure. And standard pressure is 1 atmosphere or 760 torr or 760 millimeters of mercury. That's like regular pressure, right? Normal atmospheric pressure. Easy to get. Just have your container open and it's 1 atmosphere. Standard temperature is 273 Kelvin or 0 Celsius. Why did they pick that for standard temperature? Because it's really easy to get in the lab. And remember, a lot of this stuff was done before electricity, refrigeration, anything like that. So how do you control the temperature of something when you don't have hot plates and refrigerators and things? Well, if you put your container in a big bath of ice water, it will be 0. Done. You don't even need a thermometer. As long as there's ice and water together, it'll be 0. So that helps me remember what STP is because it's easy. It was something that was easy. Stick it in an ice water bath at atmospheric pressure, done. Okay? So it's useful to use STP to compare gases. The thing about gases is there's 4 variables. There's pressure, volume, temperature, and amount of gas. And so trying to compare 2 gases that have 4 different variables is hard, right? So STP, what we do is we're going to use the same temperature and the same pressure for both of these gases, and then we can make more useful comparisons. So molar volume is the volume occupied by 1 mole of a gas at STP. So we had molar mass, right? The molar mass is the mass of 1 mole. The molar volume is the volume of 1 mole at STP. So let's calculate what that would be. So PV equals nRT, and we've rearranged this before. Volume equals nRT over P. So there are no numbers here other than the 1, which was written out. But what's the volume of 1 mole of gas? So N is 1 mole. And we're talking exactly 1 mole because it's theoretical. R is our friend 0.08206 liter atmospheres per mole Kelvin. And what's the temperature here? 273 Kelvin. If we used 0 Celsius here, our volume would be 0. And the volume of something real can't be 0. Divided by the pressure, 1 atmosphere. So moles cancel, kelvins cancel, atmospheres cancel. We're left with liters. 1 times 0.08206 times 273 divided by 1. We got 3 sig figs going on there, 22.4. That's the molar volume at STP of any gas. Any gas. That doesn't work with molar mass, right? The molar mass is different for each different compound because they all have different masses. But the volume of a gas is the same because the size of the particles don't matter. It's kind of weird. Because I said we're trying to calculate the volume of exactly 1 mole. A mole of any gas will have the same volume, which is a bit to get your mind around. So the molar volume of any gas at STP is 22.4 liters per mole. That sounds like a nice conversion factor. So a mole is Avogadro's number of molecules. So 6.022 times 10 to the 23rd molecules of a gas at STP take up a volume of 22.4 liters. 22.4 liters is a cube about this big, like a good-sized packing box. It's a liter of gas at STP. The identity of the gas doesn't matter. Different gases, 1 mole of different gases will all have the same volume, but their masses will be different. So this is a really, really convenient conversion factor for gases at STP. You can't just use it for everything. You cannot use it for liquids or for solids. It can only be used for gases. So here we have an illustration. Here we have helium, xenon, and methane gases. At STP, 1 mole of helium, 22.4 liters. 1 mole of xenon, 22.4 liters. 1 mole of methane, 22.4 liters. Now, would these balloons weigh the same? No, they wouldn't. But they would take up the same volume.
It's all 22.4 liters.
So this balloon with 1 mole of helium would weigh how much? 4.003 grams. And how about 1 mole of xenon? 131.3 grams. Now the cliche is it goes over but like a lead balloon. This is heavier. It's a mole of xenon, 131 grams. That's not going to float. We could calculate the methane too, but I don't feel like calculating something right now. Assuming ideal behavior, which of these gas samples has the greatest volume at STP? So we just learned that 1 mole has a volume of 22.4 liters at STP. But this is giving us grams. So can we just say, oh, well, grams and moles, they're all the same? Because 1 gram of hydrogen is like half a mole, right? 1 gram of oxygen is 1/32 of a mole. And 1 gram of argon is 1/40 of a mole. You could do this without calculating. So each argon atom weighs 40 atomic mass units. The hydrogen is 2 atomic mass units. So 2 AMUs. Oxygen's 32, because those are diatomic. And this one's 39, close enough, 40. So we have equal masses of these. Which one's going to have more atoms or molecules in it? Let's say I have a box that weighs 10 pounds, and this one has bowling balls, and this one has ping pong balls. Which 10-pound box has more balls? The ping pong balls, right? Because ping pong balls weigh almost nothing, and so 10 pounds of ping pong balls, that's a lot of balls, right? 10 pounds of bowling balls, that's probably 1 bowling ball. Does that make sense? So which of these is going to have a greater volume? The hydrogen. Because each of the particles weighs less. You're going to have more particles in 1 gram. The masses are equal, so the smaller particle, you'll have more particles in the same mass. Because it weighs less. Yes, there is a way to check that. So you could do the calculation. And sometimes it's actually faster to just do a calculation than break your head thinking about it. So how would you calculate that? Well, you take 1 gram of hydrogen, and using the molar mass, find out how many moles that is, and then use STP to calculate.
So will it always be the smaller one?
It'll be this in something like this with equal masses. The smaller molecules will take up more space because there's more of them. It's because there's more of them. So I don't remember where I usually put this analogy. I'm going to stick it in here right now. We used to drive cross country in the minivan with the kids. It's quite an adventure to visit my parents in Minnesota. And I remember going through Wyoming. And this was before cell phones and stuff, so we had a AAA guidebook. We were reading the AAA guidebook. And I realized that the population of Wyoming, the whole state, is about the size of Fresno without Clovis. I know, right? Spread out in this whole state. It's like 450,000 people, something like that, in the whole state. So that explained why, as night fell and we're driving along, we could drive for miles and miles and not even see one ranch light in the distance. Nothing. It's empty. There's nothing there. It's beautiful, but there's no people there. Okay, so gases are like Wyoming. You get it, right? No, not quite. So the gas particles, molecules or atoms, are the people. Okay, and the volume that the gas occupies is the state, right? So the state of Wyoming, there's very few people, there's a lot of empty space. So does it matter how big the individual people are? Whether they're all really lean and fit or they're all, big and bulky guys, does it matter? No, because there's so much empty space in between, it doesn't matter how big things are. Now, if you're talking about an elevator with 10 people on it, now does the size of the people matter? Yeah. So, we've got 10 cheerleaders in there, no problem. We've got 10 offensive linemen in there. Things are getting a little tight, right? But in a gas, because there's so much empty space, it doesn't matter. In a liquid and a solid, touchingly close, that's more of an elevator situation, then things matter. The size matters, okay? So that's why the same number of particles take up the same volume, because it's mostly empty space. Does that make any sense? So go home and tell your mom or whoever asks you, what did you do at school today? Gases are like Wyoming. That's the lesson for today. So the density of a gas. The volume of a gas the volume of a mole of gas is the same, no matter what the gas is. But its density is going to be different because its mass is different. The volume's the same, but the mass is different. So density, we've done this before. Density is the mass divided by the volume. And for gases, we usually give that in grams per liter so that we have nicer numbers rather than grams per milliliter. So you can get kind of fancy with this, which the book does, and if you want to use that, that's fine. So the mass of 1 mole is the molar mass of the gas, and the volume of 1 mole at STP is 22.4 liters. And so we could say the density is the molar mass divided by the molar volume. So that's great, but that's another equation to remember. And I don't like remembering equations. I would prefer to just keep with density as mass over volume, and then if I have to, say, calculate the density of helium at STP, I'm going to figure it out, right? So I'm going to say to myself, well, the density is the mass divided by the volume. Well, density of helium at STP, I'm not given a quantity or anything because the density doesn't depend on the amount of stuff. It's an intrinsic property, an intensive property. So this is where I just choose an amount. So it would be convenient to choose 1 mole. So when I do this, I'm going to choose 1 mole. And then I'm going to ask myself, well, what's the mass of 1 mole of helium? 4.003 grams. At STP, what's the volume of 1 mole of helium? 22.4 liters. So 4.003 divided by 22.4. So the density for helium is going to be 0.1787 grams per liter. Mm-hmm. The molar volume is always 22.4 liters at STP. Yeah, if it's a different temperature, different pressure, it's going to be different. But at STP. For 1 mole. That's why it's the molar volume, the volume of 1 mole. So how about the density of nitrogen at STP? Well, we always have to ask ourselves, is it a diatomic element? Yes, it is. So here, the nitrogen atoms are not individually going around. They're holding hands. And so they're acting as 1 particle, and it's the number of particles that matters.
And we need to know that it's diatomic because it's a gas, right?
We need to know that it's diatomic, or the reason it's important here is because we have nitrogen by itself as the element. If it was, some other gas, nitrogen monoxide or something, then we wouldn't care. But because it's nitrogen gas by itself. Helium is not diatomic, and so helium gas has individual atoms. It's important that the nitrogen is diatomic because that affects the number of particles. Yeah.
What was it again? It was this?
It was starting at 7, make a 7. Or horses need oats for clear brown eyes. So it's nitrogen is a 7, make a 7, NOFCLBRI. Plus hydrogen because he's weird and is an exception to everything. So this is N2. So what's the mass of 1 mole of N2? It's 28.02 grams. And what's the volume of 1 mole? 22.4. So 28.02 divided by 22.4. 1.2508 grams per liter. The densities are different. If I calculated the density of nitrogen atoms, it would be half as much as the nitrogen molecules. So what if it's under some other conditions? Well, you can also come up with an equation for that. So the book uses this. Density is the pressure times the molar mass divided by RT. And like I say here, this equation is valid, but then you have to remember it. So I think it's better to just remember the density equation, which we've learned already. Density is mass over volume, and we're just going to use the gas laws. We're going to say I'm going to choose 1 mole of gas, because that's easy. And then I can calculate the mass of 1 mole, and I can use a gas law to find the volume of 1 mole. So calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. So it says calculate the density. So I say to myself, well, the density is the mass divided by the volume. So I need the mass of this gas and I need its volume. And I'm not given an amount. So this is where I choose something that's going to be easy. If you want to choose something hard, go right ahead, but why? Choose 1 mole. So what's the mass of a mole of xenon? It's on the periodic table, right? 131.3. Xenon's not diatomic, so we don't have to multiply by 2 or anything. And I'm going to use the ideal gas law to find the volume of this gas, because this is not STP. So I'm going to divide by pressure. The volume of the gas is nRT divided by P. Well, what's N? I decided that it's 1 mole. Okay, choose 1 mole. So I have to pick an amount to find the mass and the volume of. So I picked 1 mole because it makes lots of things easier. So the amount of gas is a mole. R is always the same, 0.08206 liters times atmospheres divided by moles times Kelvin. The temperature, well, they gave me the temperature in Celsius like they so often do. I need to convert that to Kelvin. .318. Kelvin. And all of that's divided by the pressure. Can I use millimeters of mercury in my equation? No, because the gas constant has atmospheres. So 742 millimeters of mercury times 1 atmosphere per 760 millimeters of mercury. So down in the bottom here, 0.97631 atmospheres. Atmospheres cancel, kelvins cancel, moles cancel. .728 liters. Now this is not at STP, but it's not crazy different from STP. And so we get this volume here of 26, which is in the ballpark of 21, or 22, so we can feel pretty good about that. If I ended up with 0.7 liters of gas or 5 gazillion, I'd have to check my math. So that's the volume of 1 mole of this gas under these conditions. So I plug that into my density equation. I end up with 4.9124 grams per liter. 4.91 grams per liter. The density of a gas will change when you change the pressure or the temperature, because it can expand and contract. Its mass doesn't change, but its volume changes, and so its density can change. We're doing exactly the same math ultimately as using that equation. It's just the approach is a little different. I think it's better to take pieces that we're already familiar with and put together instead of learning new equations. You would always use ATM because of the ideal gas constant. So if you've got R in there, the units on R tell you what you have to use for the other units.
So, for example, if you had moles but you didn't have Kelvin, would you put 270 Kelvin?
So if I had moles but not Kelvin,
Or you even have atmosphere, would you put 760?
so they have to tell me something about the temperature and the pressure. If they say at STP, then it's 273 and 1 atmosphere. If they don't tell me, then I can't really solve the problem. Yeah. So I really got on you last week about the density calculations and how I wanted you to learn to do density calculations using density as a conversion factor. And several of you that went through that process and did what I asked came to me and said, oh, that's a lot easier than doing the density equation. And I tried to be gracious and not say, I told you so, although, I did. I told you so. But that does not mean we never use the density equation. We use the density equation when we're calculating the density, right? Because there's no way to do unit conversion to calculate the density. Density is mass divided by volume. But if you have a density and you're doing other things, use the density as a conversion factor. It really is simpler. And if you still don't believe me, I would encourage you to come challenge me during lab and we can have a nice discussion about it. I think I'll win, but maybe I won't. 4.91 grams per liter. Okay, so here's one where they're giving us the density and asking us to calculate something else. The density of a gas is 1.43 grams per liter at a temperature of 23 degrees Celsius and a pressure of 0.789 atmospheres. Calculate the molar mass. So I would approach this by asking myself, well, molar mass, what's that? So we sometimes abbreviate this capital M, capital M. So that's the mass in grams divided by the number of moles, right? It's units on grams per mole for molar mass. So then here, what I need to do is I need to pick an amount of gas, because here again, molar mass doesn't depend on how much stuff we have. I'm going to pick an amount of gas and find its mass and how many moles. So it'd probably be easiest again to just choose 1 mole. So I'm going to choose 1 mole of gas. And I'm going to find out how much that 1 mole of gas weighs under these conditions. So that's my N. N is 1 mole. What's P? Pressure? 0.789 atmospheres. And the temperature is 23 degrees Celsius, but we have to convert that to Kelvin. That was wrong, 273 Kelvin. $296. So I have N and P and T, and I know what R is, so I can calculate the volume of this. One mole, the ideal gas constant, the temperature, and the pressure, 0.789 atmospheres. Atmospheres cancel, moles cancel, kelvins cancel. So the volume of 1 mole of gas under this set of conditions is 0.08206 times 296 divided by 0.789. 30.785 liters. Up here, what I want, I need grams and moles. I picked 1 mole. So I need to take this volume and change it into a mass, and that's where I'm going to use the density as a conversion factor. Because what that means is 1.43 grams is equal to 1 liter. Like 1 inch equals 12 feet. No, 12 inches is 1 foot. Or we could write it as a vertical fraction. Whichever one makes more sense to you in terms of a conversion factor. So I can convert liters to grams, put grams on the top and liters on the bottom. 1.43 grams is equal to 1 liter for this problem. So the mass is 44 grams. And so that just is 44.0 grams per mole. But this is the problem-solving thing again. Being able to take pieces that you're familiar with and put them together in a new way, right? And we end up doing stuff like that in life because, there's just so many situations that come up in life, and you have all the tools to get through whatever it is you need to do, but you've never actually done that exactly that way before. 44 grams per mole. Another conceptual problem. Arrange the following gases in order of increasing density at STP. We've got neon, chlorine, fluorine, and oxygen. So let's think about this. So density is mass divided by volume. What do we know about the volume of a gas at STP? 22.4 liters is 1 mole. So if I had 1 mole of each of these gases, they would occupy the same volume. But what's different? Their masses. So if they all have the same volume, which one's going to have the highest density? The one with the highest or lowest mass? The highest density, the highest mass. The lowest density, the lowest mass? Yeah? So which one of these weighs the most? There's not much space up here, so I'm just going to do it down here. So neon's easy, right? It's 20. And oxygen is 2 times 16, 32. And fluorine is 2 times 19, 38. And chlorine is 2 times 35.45, so about 70. This is one place where we can round off these masses because we're not actually calculating, we're just putting them in order. So, which is going to weigh the most for an equal number of particles? The chlorine, right? So, and this is a type of problem that a lot of students have trouble with. It says arrange the following in order of increasing density. I assume that they taught you how to do stuff like this, put things in order. I don't know what they taught you. Increasing means that the thing at the beginning is smaller, and then you get bigger and bigger and bigger, increasing to the end, right? And then these greater than, less than signs, that's also confusing for a lot of people. This is how I remembered it when I was a kid. So this is the small end, and this is the big end. That makes sense? So the big number goes on the big end, and the small number goes on the small end. So this is saying that the thing on this end is greater than that. And if we were using these same two numbers, we'd have to put 10 is greater than 1. Okay? Little math review there. So this is neon's the smallest, then oxygen, then fluorine, then chlorine. So we need to pick the one that's correct. Well, instead of trying to evaluate each of those, it might be best to just write it out ourselves and then find the one that matches. Which of these is the smallest? Neon. So neon first, and then the next biggest is oxygen, and the next biggest is fluorine, and the very biggest is chlorine. So then I need to find the one that matches up, and that's going to be A. Yes? Yeah, that is confusing, isn't it? So here we're comparing, we're taking essentially equal volumes and saying which one weighs more, right? And so the one with the heavier particles is going to weigh more, and so it'll have the higher density. With the previous problem, we were taking equal masses and trying to figure out, well, which one has more particles, so which one would take up more volume. Yeah. So they're kind of similar, but they're not. Right. Yeah. Any other questions? Yes.
We don't know the volume, we're just assuming it's all the same.
Right, we're not given a specific volume, and it's not necessary because the density of a gas is the same whether you have a liter of it or 10 liters of it, or 50 liters. The density doesn't change with the amount of substance. In order to compare these densities, because it's the relationship between mass and volume, it's helpful to have one of those things be the same and then compare the other thing. Yeah. So we can also do things like this where we can find the molar mass of a gas experimentally without using technology. We have a mass spec in the next room, and that'll find the molar mass of anything you want, but it's a fancy, expensive piece of equipment. For a volatile liquid, and volatile means that it evaporates easily, we can take a sample of that liquid and heat it so that it becomes a gas and fills the container that it's in. So then we know the volume, and we can measure the pressure and the temperature when it's the gas, and then we cool it down so that it condenses back into a liquid, and then we can weigh it. So we can measure the temperature, the pressure, the volume of the gas. From those pieces, we can get the moles of gas, and then with the mass, we can figure out what the molar mass of a gas is. And again, you can make a fancy equation for this, but then you have to remember the equation. So molar mass is grams per mole, the mass divided by the number of moles. So let's do an example here. And we're going to actually do an experiment where we do this in lab too. A sample of a gas has a mass of 827 milligrams. Its volume is 0.27 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. Find its molar mass. Well, let's pull out this information. 827 milligrams. What's that? It's mass, right? So that's the mass. And then it says the volume is, so volume is 0.270 liters. The temperature is 88 degrees Celsius. And the pressure is 975 millimeters of mercury. We want to find the molar mass. Molar mass is the mass in grams divided by the amount in moles. Grams per mole. Well, we've got the mass in milligrams, so we can convert that to grams. Milligrams on the bottom, grams on top. Milli means 10 to the minus 3, so I've got 1 times 10 to the minus 3 up here and 1 down there. And so this is 0.827 grams. So that's the numerator, 0.827 grams. And now I need to know how many moles of gas. Ideal gas law. PV equals nRT. We're finally going to solve for something besides P and V. I'm going to solve for N. So I'm going to divide by RT on both sides. So the R's cancel out and the T's cancel out. So the number of moles is equal to the pressure times the volume divided by R times the temperature. We've got R here, so we need liters, atmospheres, and kelvins. Well, the volume's fine, but the temperature is not. We'll convert that to Kelvin. 361 Kelvin. And then the pressure needs to be converted to atmospheres. So 975 divided by 760. 1.2828 atmospheres. Now that I have the correct units, I can plug these into my equation. The pressure is 1.2828 atmospheres. The volume is 0.270 liters. R 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature, 361 Kelvin. The units work out. We end up with 1 over moles, which is the same as moles. Now, when you put this into your calculator, you need to be very careful because there's a really, really common mistake. We tend to see this as 1.2828 times 0.27 divided by 0.08206 times 361. But if we put times here, our calculator is going to finish the rest of the math, and this 361 is going to end up in the numerator instead of the denominator. So if you want to do that, which a lot of students just really want to do. But it's times. Then you have to use parentheses. Parentheses, times, parentheses. So get your calculator out and make sure that you can get the same answer. Because it's great to be able to write the formula out, but if you can't make your calculator give you the right answer, you still get it wrong. So 1.2828 times 0.270 divided by, we use parentheses because that's what students like, 0.08206 times 361, close the parentheses, equals 0.011691 moles. It's a weird zero. The other way you can do that is 1.2828 times 0.27 divided by 0.08206 divided by 361. That's how I do it. Or if you want to see this as multiple terms, this divided by this times this divided by that, you have to figure out what works for you so that you can get the right answer.
So you put 3 sig figs?
I've got 3 sig figs, yes. Because of all the things that have 3 sig figs. The temperature only had 2, but when I added, it got 3. That happens a lot. So then I'm going to take that amount of moles and stick it up here. And I've got 0.827 divided by 0.01169. .7 grams per mole. Is that a reasonable molar mass? Well, how do we even know? What would be an unreasonable molar mass? -7? Yeah, that was totally ridiculous. How about 0.5? What's the smallest atom? Hydrogen. If you have hydrogen atoms, not the diatomic hydrogen molecules that you would actually have, but hydrogen atoms, that would be 1 gram per mole. So if you ever get anything that's less than 1 gram per mole, something is wrong. And if you got, 542,000 grams per mole, that would probably be bad too. Yeah. This actually is reasonable. Any questions? So here's an example that's more like what we're going to have in lab. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask and puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. Now that's a story problem. And there's a story. It's kind of a boring story, but it's a story. Got a character and, I don't know, not a big plot, but... So what are we trying to find? The molar mass. So then, well, what does molar mass mean? It's the mass in grams divided by the amount in moles, right? So we're looking for grams divided by moles. So they didn't give us anything directly. Can we figure out the mass of this gas? What's the mass? How do we figure it out? Subtract. And some of you are still struggling with this, and I get it, because this chemistry is very abstract and weird and different and just scary in some ways. But let's not panic. Let's just put our thinking caps on And look at the words here. Mass of flask plus gas. Mass of flask. If I look at the words, which typically are friendlier than numbers, and I want the gas by itself, I need to get rid of the flask. Right? This is both of them together, and this is just the flask. So that helps me know that I need to subtract. So 78.416 grams minus 77.834 grams. That gives me the mass of the liquid. I do not care at all about the mass of the flask. It was only necessary because I couldn't get the gas the liquid to stay on the balance pan. So that many grams. Okay, so that's one thing I need. That's the mass. 0.582 grams. The other thing I need is how many moles of gas do I have? So that's an ideal gas problem. So we rearranged the equation in the previous example. So we had the moles equals PV over RT. We've got R involved, and so we need to have liters, kelvins, and atmospheres for our units, and of course none of them are right. So we need to convert milliliters to liters. Milliliters on the bottom, liters on top. 1 milliliter is 1 times 10 to the minus 3 liters. So this is 0.213 liters. Here the temperature is 100.0 degrees Celsius. It was measured more precisely. This would be a good time to use the full 273.15. So that's going to be 373.15 Kelvin, with that first decimal place being the last significant figure. And then we've got torr. Remember, torr in millimeters of mercury, same thing. I need to convert to atmospheres. 1 atmosphere is 760 torr. .9921 atmospheres. So now I can put these numbers into my equation. The pressure is 0.99210 atmospheres. The volume is 0.213 liters. R is 0.08206 liter atmospheres per mole Kelvin, and the temperature is 373.15 Kelvin. Atmospheres cancel, Kelvins cancel, liters cancel. So again, be careful on your calculator. So it's 0.0069 moles. If you got 960 moles, you made a calculation error and multiplied by the temperature instead of dividing. It's easy to do, but it's important not to do that. So then I put my moles up here. So 0.582 divided by 0.0069011 84.3 grams per mole. Reasonable? Yeah, it's greater than 1 and less than a whole bunch. Any questions?